Good. The first speaker is Tsvi Piran.
The questions that I want to ask, and of course if I ask them the answer will be yes, is this a smoking gun proof to what is the origin of gold? And by gold I want to stress that I like the word gold because we all have some gold and it's a very popular concept, but by gold I mean heavy elements with atomic weight larger than 100 or 130. The borderline is not so strong, but so it's all heavy elements, all elements which are considered as rare elements. So you can add to this plutonium, uranium, platinum, whatever. And the second question, does this assure us the identification of electromagnetic counterparts to gravitational wave sources, something which is very important, as you remember from David's talk yesterday. So this is the outline of my talk. I'll mention gravitational waves, then I'll talk about gamma ray bursts, then I'll introduce this concept, which is not so well known, the Lipachinski-Macronova. Then I'll discuss nucleosynthesis, because after all I want to produce gold. And then I'll put it all together in this event, which was involved with gamma ray burst 1306-03b, and conclude with some implication to the origin of gold. And then there'll be a big question mark at the end of this. Is this just one big speculation? So I'll come up with two positive confirmation from this burst and from plutonium abundance, and with a tentative future confirmation of this whole idea. So this is the outline of my talk, and I hope that I'll be able to cover all this in this 35 minutes. So we all know that binary pulsars rotate around each other like other stars, but because they are near and point sources, they emit gravitational waves, and this was confirmed by Jules and Taylor in this beautiful observation of the shrinking of the orbit. So we know that gravitational waves exist, at least indirectly, but the goal now is to detect these gravitational signals directly, and there is huge effort, which we heard about yesterday from David, about detecting this directly, and hopefully these signals, this chirping signal from compact binary mergers will be detected sometime in the next 3 years, sort of in celebration of 100 years for the prediction by Einstein of the existence of these gravitational waves. So this is the major goal in the astronomical gravitational wave community. But suppose that we detect such an event by with the gravitational wave detector. Of course, it will be a great victory, but from an astronomical point of view, it will be a huge challenge. And the challenge is that this has the localization, for example, from the first two detectors, has an error of about 275 square degrees. And this is a slide that I borrowed from Samaya. And you can see here as an example the size of the moon, which is only 0.25 square degrees. So this is this size on this scale. And we have to search now over such a region to see where is the object. And we don't know. And if we do not find the electromagnetic counterparts, then as beautiful as the detection will be, from astronomical point of view, it will not tell us much, unfortunately. That's a sad thing, but we have to find the counterpart. Now, it's an interesting fact that in 1993, we pointed this out, and this was accepted by complete rejection from the gravitational wave community. They didn't want to hear about accompanying electromagnetic signal. No, this is not important. Detection of gravitational wave will be done on its own. This was the reaction of the community in '93. I am very glad that after 22 years, to hear the huge effort now in which the whole astronomical community is geared together with the gravitational wave community to search for counterparts. But what are these counterparts? Well, the most natural one is gamma ray burst. Once or twice a day, we see a burst of gamma ray burst with a huge energy input, about 10 to the 51 ergs in a few seconds. And this is a possible counterpart. Now, just to remind you again, all the history, in the late 80s, textbooks were clearly stating that gamma ray bursts are coming from magnetic flare on galactic neutron stars. And a side remark, at the same textbooks, it was also mentioned that all nucleosynthesis takes place in supernova. Now, we wrote a provocative paper at that time, at 89, suggesting that neutron star mergers producing gamma ray burst, and they also produce gravitational waves, of course, and they also produce a heavy R process material. So this was in complete contrast with the accepted dogmas at the time, and surprisingly it was accepted by nature. Not surprisingly, again, this paper was ignored for at least 5 years by the whole community. It's amusing to see that there is not a single reference to this paper for the first 5 years after it was published. By now, 2015, we know that gamma ray bursts are cosmological, and we know that from studies of supernova nucleosynthesis that there are serious problems with producing the heavy R process elements in supernova. So these two standard models which were there do not work, and we have to think about something else. For gamma ray bursts, we know that there are two types, long and short. The long ones are associated with collapsars, collapse of a massive stars, and a jet comes through the envelope and penetrates the envelope and so on. There's direct evidence because of association with supernova. There is a lot of indirect evidence that support the idea that the short gamma ray burst, those that are less than 2 seconds, arise from a completely different process, and all the indirect evidence suggests that they are compatible with binary neutron star mergers or compact or black hole neutron star mergers. So there is a lot of indirect evidence. There is no direct proof. So can we use them as our counterparts? Unfortunately, we know that the gamma ray bursts are beamed. They're beamed, and therefore we have only 1 in 10 chance in detecting them. The beaming factor is actually probably narrower. The beaming factor is only 1 to 40, but there is this effect that if the jet is pointing towards us, then most likely this is the direction in which the gravitational wave signal is strongest, and therefore the horizon in this direction is farther out. And if the horizon is farther out, we are more sensitive to this orientation. So it's not 1 to 40, but 1 to 10. But still, this means two things. First, we have to keep GRB satellites like SWIFT into the era in which gravitational wave detectors are operational, because there's still significant chance that we'll detect such a counterpart. But the second thing that it tells us that gamma ray bursts on their own are not enough. And for people who are more familiar with the details of gamma ray burst, we can also have what is called off-axis afterglow. So you can have a gamma ray burst which points out in this direction, but there will be afterglow seen also from that direction. Unfortunately, this off-axis afterglow is too weak, so we cannot count on it. So we have to look for something else. Now, numerical simulations of mergers have shown that and this is a simulation from Stefan Rosswog, but there are a few other groups doing it, the one of Janka at Munich, the one of Masaru Shibata at Kyoto, and of Rezola at Frankfurt. This is the main group, but I'm sorry if I forgot a few others. But I just picked this simulation because Rosswog is a close collaborator. And what is important here in this simulation is what you've seen here. I don't care at this particular moment about what happened here in the merger itself. I care about the stuff that you see here. And the point is that the mergers eject a lot of material, about 0.1 to 0.04 solar masses with very large velocities, about 0.1 c, maybe more. So the kinetic energy involved is fairly large, about 10 to the 50, 10 to the 51 ergs. So this is the source of possible electromagnetic counterparts. And there are now a lot of much more detailed work about other sources of ejected material. This is just the main source, what is called the dynamical ejecta. But there are now a whole list of sources that I can list. Neutrino-driven winds from disks and material coming from a cocoon due to jet wind interaction and so on and so on. But what is important is just the basic fact here that a lot of material is ejected out. Now, in '97, Lee and Paczynski proposed the following simple idea. This material will be radioactive. It will emit something like 10 to the 50 ergs in radioactive decay. This is the expected energy. And this will produce something which looks like a weak, short supernova. Weak and short because the energy, the position is smaller and the mass is smaller, but it will be something like a supernova. Later on, Shri Kulkarni gave it the name Macronova. Other people called this kilonova, but because the argument was that this is exactly 1,000 times the light of a nova. However, this was in 2000. Now, more recent calculations have shown that it's only 100 times stronger than a nova. So maybe we should change the name kilonova to hectanova. And maybe if we do some further calculation, we will find it's only 10 times stronger than nova. Then we'll have to change it to decanova. So in order to save all this, I suggest to stick to macronova and not commit exactly on an energy budget that we don't exactly know. So I'll stick to this name Macronova, but if you hear kilonova, it's the same thing. Now, the input is the radioactive decay. This was first calculated by Freiburg-Gauss in '99 and later by Korobkin and many other people that I didn't list here. But basically, the input, which fairly follows what the original ideas of this work was that after a short period of about 0.1 seconds, there is a decay in the input as a power law as t to the minus 1/3. You don't get the usual exponential decay that you see for nickel because what we have here is a mixture of different isotopes. And when you have a mixture of different isotopes, you get a power law instead of an exponential. And actually, there are some theoretical ways to derive more or less this factor of t to the minus 1/3, but I won't go into it here. So what we have here, we have a matter which is expanding, and the center is optically thick, so we can't see it, but the outer region is optically thin, so radiation escapes from this outer region, and we have increase in the light curve, and then when it becomes completely transparent, we get the maximum light, and then there's a decrease, and the decrease is simply because of the radioactive energy input, which is decreasing with time, and the light curve depends basically on three quantities: the mass, the velocity, and the opacity. We have to know these three quantities to figure out what is the light curve here. And this is one of many calculations of light curves which you've done. And you see that the intensity here is somewhere between 10 to the 40 to 10 to the 41 ergs. As I said, this is about 100 nova, not 1,000 nova. And it depends on the viewing angle and some more details. But it's basically, this is the basic intensity. And it's important to figure out that with the opacity as we understand it now, this emission will come in the infrared. And this was actually very fortunate because Kaysen and Barnes noticed a correction to the opacity, which will put it in the infrared rather than in the optical. And they noticed this just in the fall of 2012, winter of 2013. So there was a realization in the community that the opacity is much larger, and because of this, the emission will be in the infrared. So the idea that the emission is the infrared came before the observation. Otherwise, if we observed in the infrared and while we expect it in the optical, and then we correct it for the opacity, it will be like, like an epicycle. But there was a prediction clearly printed out that the emission of a macronova will come in the infrared before this observation that I mentioned before. So let's go to the next step, which is nucleosynthesis. This is a compilation of cosmic abundances, and gold is here, and we are interested in this region of the heaviest element, and the question is how are these elements produced? Basically, there are two processes, actually three, but the two main processes, the S process, the slow process, in which you go from light material and light elements and slightly adding neutrons one by one, or there is a rapid process, and in the rapid process you add a lot of neutrons at once, and then you produce a very radioactive, unstable isotope, and then you let it decay to the value of stability. So this is the R process. So this is how the R process looks like. You start from here, from the light elements. You have a huge flux of neutrons. And if you have a huge flux of neutrons, all the neutrons are absorbed by the atoms, and you reach elements which are here. This is the value of nuclear stability. This is the number of protons. This is the number of neutrons. This is the stable nuclei. So you get to here. This is a very unstable region and unknown region. This is a region that we don't explore in any way on Earth, so we have to rely on some extrapolations and calculation to figure out what is going on there. But basically, it is clear that the principle is clear. The details are subject to speculations and approximations. That neutrons will be absorbed, produce isotopes which are very, very heavy, with a lot of neutrons and few protons, and then the neutrons will decay and reach the value of stability from here. And there are some elements that you can prove in nature that this is the only way that they can produce, because there is an unstable element. If there is an isotope here and there is an unstable isotope here, you cannot get to here by the slow process. You must go like this and reach it by the fast process. So this is the rapid nucleosynthesis, and the decay of a neutron star matter is a classic place for this process to take place, because you have all these neutrons. So by definition, you're neutron rich. You have this huge flux of neutrons, and all that you have to do is to take this to take this box of neutrons, let it expand, and then calculate the nuclear reactions and find the final abundances. I'm saying all that you have to do, but this is a tough work, and this is some calculation like this, again from Korobkin, but other people have done it. What you see here is a function of time. This is the heating rate. This is the abundance. You see that the material goes to here, and then it decays, and eventually settles down to this value of stability. And this is the final abundance. And several groups have repeated this, and a remarkable result that arises here is because the conditions are very uniform. We take neutron star material, we throw it to space, all the processes are the same. We get more or less the same abundance pattern every time that we do this, and surprisingly or not, this abundance pattern agrees more or less with the observed abundance in the universe. So it seems to work, but we have to ask, does it happen in the right rate and in the right amount and in the right quantity? So is this really working or not? So I've talked about four different topics: gravitational waves, gamma ray burst, and nucleosynthesis and Macronova. And now I want to put it all together in one event, unfortunately without the gravitational waves. The gravitational waves were the driver possibly for pushing the system together, but we don't know. We haven't seen the gravitational wave there. But what we saw was we saw short gamma ray burst, classical short gamma ray burst. And it was at a distant galaxy, but not too far away, at the redshift of 0.356, very convenient for the calculation, at just 1 gigaparsec. Please notice that it is farther than the typical horizon of LIGO Virgo. So from a point of view of LIGO Virgo, this was undetectable, but because of the fact that we had a localization from the gamma ray burst, we could find the host galaxy, and then these were the observations that were done 9 days later. This was actually 6.6 days later in the source frame if we take into account the cosmological redshift. So this is the figure that I've shown you before. There is nothing here in the visual, and there is a near infrared signal that we see. So the basic observation was a near infrared signal with no visible light. Now, what should this be compared with? This should be compared with the GRB afterglow. Gamma ray bursts have a long-lasting afterglow, both in X-rays and in optical and in infrared in radio. So the first question to ask, does it fit the afterglow? And then the answer is no. This is the optical afterglow. This is an upper limit here. This is extrapolation from the earlier measurements. This is the infrared afterglow. And again, this is extrapolation from the earlier measurements. And this is the observed point here. And what you see superimposed on this is a calculation of a Macronova calculation. This particular calculation were done by Kenta Hotokezaka. So it is, and they were done again before the burst was done. You have to adjust the mass ejection, and here you need a fairly large mass, about 0.4 solar masses, which is rather at the high end of what you expect from neutron star mergers. But apart from that, it sort of fits. So is this a Macronova? We don't know. Everything so far is based on this single data point, and unfortunately there is no more. This is what we know. So we are left with a guess, and you can say, oh, of course, this is nonsense. And I can also tell you that there are other possibilities. There are other models and other ways that you can fiddle out with the afterglow mechanism and produce such a flare. So the answer is maybe yes, maybe not. But let's proceed assuming that this is correct. And here I come to the one topic before last. The question is, what is the origin of gold? And again, I want to stress that by gold I mean heavy R process material, all the heavy elements. We can do a simple calculation, a trivial calculation. We can take the rate of the events, and this is here per mega year, and we can take the number of the mass which is ejected per event of our process material. And we should calculate that the product of the total mass ejected, which is the total mass produced, which is the product of the rate time the mass ejected time the Hubble time, should be equal to the amount of heavy R process material that we have in the universe. This gives us, not surprisingly, a straight line. The reason that I've shown here 3 straight lines and not just one is, first, there is uncertainty in the total amount of our process material, but in addition to that, there is a question whether the rate, which I plot here, this is the rate now at time 0, is constant with time. So there are 3 lines here, one assuming that it's constant in time, one assumes that the rate in the past was 3 times larger, and one assumed that the rate in the past was 5 times larger. Now, if the events which are producing the R process material are supernova, they follow the star formation, and we know that the star formation in the universe was larger in the past. But we also know the same thing for short gamma ray bursts. This is the rate, the expected rate of short gamma ray bursts. There's some uncertainty on the high end. This is the redshift, but we know that it is falling in the present universe. It's decreasing with time by about a factor of 5 from the maximum at about redshift of 1 to now. So this is why we took these 3 lines. And also marked here is the Macronova range of mass ejection between 0.01 to 0.1 solar masses. And we see that there is a nice intersection between this region and the range of rates of neutron star mergers estimated either from the rate of short gamma ray burst or from the rate of galactic neutron star mergers. So this is the rate of galactic neutron star mergers. This is the rate estimated by short gamma ray burst. This is the rate of masses expected to be ejected by Macronova. And there's a nice intersection here between these rates and the R elements, the heavy R process elements material in the universe. So this is a possible solution. The other solution, the standard solution, which was standard up to some time, was that everything is produced by supernova, and Kolkora supernova rate is somewhere high about here, so with a very small mass ejection per event. But so this is very nice, but the question is, can we break this degeneracy that we have here between rate and yield? Can we break this degeneracy in time? And I'll show later that this can be done. So let me make a short summary. If these observations are correct, then it confirmed that the idea that gamma ray bursts or short gamma ray bursts are produced by neutron star mergers. It confirms the idea of Lipachinski supernova, and it confirms that compact binary merger are the sources of heavy R process material. So if this observation is, if the interpretation is correct, the observation is there, but if the interpretation is correct, it has dramatic implication on 3 different topics. So can we confirm this? So I'll make now remarks about 3 different things. First, we can wait for the next short gamma ray burst to take place. Strong enough short gamma ray burst takes place about once per 2 years. So 2 years have passed. It's about time that we get another one, and I'm sure that by now there'll be more Hubble time to follow it up more carefully. But we can do something else. We can go backwards to archival observations of gamma ray burst and try to find whether there was another evidence for event like this in the past. And this is exactly what we did. And this was a puzzling gamma ray burst. It was called the long-short GRB. It has peculiar properties. But the important thing was that we found that, again in Hubble data, that there is this peak here, and this peak here, even though it looks very small, it's more significant than the previous bump that we have seen if you do detailed statistical analysis of the errors involved. So also here we see a Macronova signal. This one is at about 13 days after the burst. We don't know the redshift, so it is more difficult to tell what is the local rest frame, what is the local time, but which is important. But still, if we guess, this involved, if it was Macronova, it involved ejection about 0.1 solar masses. Now, when I first saw it, I said, no way. There is no neutron star merger that produced so much dynamical ejecta. However, if you have a neutron star black hole merger, this is reasonable. So if this interpretation is correct, it confirms the previous observation, and it also suggests that we have seen a black hole neutron star binary merger in this particular event. Again, there's only one critical observation. This is this HST data, and there is a big if involved with that. But there's another clue. And I already asked the question, can you break the symmetry here between high rate, small yield, and high yield, small rate, low rate? And surprisingly, the answer is yes. And the answer is yes if we go to radioactive elements. Radioactive elements, of course, decay. And since they decay, they track the local event rate and not the integrated global event rate. So if we find a suitable radioactive element, we can do much more. Now, if you have rare events, then a radioactive element abundance will look, this is a function of time, it will go up when the event is around us, and then it will go down, and there'll be long period of very low intensity and short period of very high intensity. If the events are very frequent, then you don't care that much about the decay. You care because it reduced the amount, but you'll be in a steady state, and you more or less always measure the same flux. So nature provides us with just the right elements for that, which is plutonium-244, which has two fantastic features here. First, it has just the right half-life time, which we need, about 81 million years, which is not too short and not too long. But the second feature is even more important. We can measure its abundance on Earth, and more than that, we can measure its abundance on Earth in two different epochs. So there are measurements of the plutonium abundance in the early solar system, just shortly after the formation of the solar system. And there are measurements of the plutonium accumulation now. Plutonium is accumulated on Earth through cosmic dust that penetrate the solar system. It penetrates the solar system, falls on Earth, and settles down at the depths of the ocean. And there are different ways of measuring it at the depths of the ocean. And these are extremely difficult measurements in which you dig a sample at the depths of the ocean and find some kilograms of material. And within these few kilograms of material, you identify one or two plutonium active plutonium isotopes, and you are extremely happy because this is a measurement. So this was done by Wellner et al. For the current sediments, and this was done earlier by another group at Caltech in a completely different method for the abundances of the early solar system. And the interesting fact, which already gives you a very strong hint, that in the early solar system, abundance was much higher than the abundance now. So the first hint is large fluctuation, and large fluctuation, it tells us that it should be rare. But you can do something much more quantitative, and this is the quantitative measurement And we see here, this is the region which is allowed by the plutonium. And this is the overlap with the rate which are coming from neutron star mergers and from Macronova. So it all agrees more or less in the same region. And it gives completely independent indication. It doesn't prove that these are mergers. It proves that there are rare events with large yield. And you like it or not, it's in the right region with this. The implication for gamma ray burst that the rate of gravitational wave detection within 200 megaparsec will be less than 30 events per year, because this was on the low end of the range here. But so the bad news. The good news is that there is a lot of matter ejected, so there will be a strong chance to detect the Macronova. The last thing which I won't have time to go in, I see that the chairman is already standing. Even so, I propose to give you some 10 euros for 5 minutes, but you. So the last thing is the following. We cannot go back in time, and we cannot do more Hubble Space Telescope measurements on these two events that have been there. But we can go back in time in a different way. Because together with the Macronova, there will be another signal which is coming from the interaction of the material with the surrounding matter, which we call the radio flare. This is something that we proposed in 2011. So there will be a radio signal, and this radio signal will be on a fairly long time scale. It should last several years. So if this was a Macronova, if there was in these two events, we have a good chance of detecting them still now. And right now, we are actually involved in searches for this event. Unfortunately, the detection is marginal, so we are not assured that we will detect them, but there is a chance that we will detect radio waves and we'll confirm it. So this is the third way for confirming this. Hopefully, this will be done into the future. Unfortunately, if the answer is negative, it doesn't rule it out. It just means that it was probably too weak. And I'll conclude here with the summary that the standard, an argument against this idea of R process production by binary mergers is that there is evidence for R process in very low in stars with very low metallicity. And in these stars with very low metallicity, so these are supposed to be very early stars which were formed very early, and they are, how can you have metals there? In fact, it depends how you look at this evidence, because if you look at the low metallicity stars, you see that they have very large fluctuation in the ratio of our process material to regular material. And this very large fluctuation are exactly indicative of a process like one that I said here, which is rare with large amount of material. So if the star happened to be near an event like this, it has a lot of material. If it was far, it has less material. The question is about the history of neutron star mergers, how early you can get neutron star mergers in the universe. This is a not clear issue. From gamma ray bursts, we don't see the mergers far enough into to identify what was the rate of these mergers at very high rate, at very high redshift. So it's really up to speculation. You have to speculate something about the rate of neutron star mergers at very high rate, at very high redshift, and depending on the speculation, you may or may not be able to do it. The question was, what is the effect of gravitational waves here on these mergers? And there are a lot of speculations about the role of magnetic fields in producing the jets that we see in gamma ray bursts, because many models for producing the jets use magnetic field as the driving force that produces the jet. But what I was talking here was particularly not about the jets, but about matter which is dynamically ejected during the interaction. This dynamical ejecta is produced even before the stars are approaching each other. It's very similar to any dynamical stream that you see in any gravitational interaction. And at this stage, even if the neutron stars are magnetized, the magnetic field are not important enough to influence the dynamics.
Okay. Thank you again, Tsvi.